PPO. PPO is the, even these days, very widely used algorithm for reinforcement learning. And I guess your final project will be also based on PPO. But today we will study what are main problems of the policy gradient. We study policy gradient. It was good, better than DQM because it can handle continuous actions, and we proved that we proved some connection between maximizing value function and the gradient in policy function are relevant. But there are some problems, so we will study what are problems in policy gradients and how can we address them. And then next time we will study detailed algorithm of PPO. And let's recap the policy gradient. So the policy gradient algorithm tries to solve the optimization problem. As you can see, we'd like to maximize value, right? Maximizing value. By taking stochastic gradient ascent on the policy parameter theta using the policy gradient. So this is just I think you're familiar with this equation. This is just a definition of policy gradient. We made a connection between gradient of value function and gradient of policy function. So even though we only have policy function, we can optimize it in the direction of maximizing value function. But there are some limitations in policy gradients, unfortunately. The major limitations are, there are two major limitations. The first one is sample efficiency, and second one is distance discrepancy. So sample efficiency is poor, and distance in parameter space is different from distance in policy space. So we will study this in detail. So let's see what is policy spacing first. So policy space is not very, it is not very special thing, just some space that a policy function is spanning. For example, in this kind of tabular case, there can be some matrices, right? Tabular case means action and state are discrete. So some space that a policy function is spanning could be some table, right? So where dimension is just a number of state, a number of action. And policy gradient takes steps in parameter space. Step size is hard to get right as a result. So let's see detail. So there are two limitations in policy gradient. The first one is sample efficiency, and second one is distance discrepancy. The first one, sample efficiency. So we studied replay buffer in DQM, but actually we haven't learned replay buffer in policy gradient. The policy gradient is on policy learning strategy, so that it actually do not have replay buffer, unfortunately. So the poor sample efficiency make policy gradient method significantly more time consuming and computationally expensive compared to off-policy method that utilize a replay buffer. We will study this also detailed next slide, but sample efficiency is telling that policy gradient is good, but unfortunately, because it's the on-policy method, it is significantly more time consuming, computationally expensive. And distance discrepancy, what does this mean? In one sentence, it's just this one. Distance in parameter space is different from distance in policy space. We know the parameter space and policy space, right? Parameter space is just, the policy function consists of some learnable weights, right? So there can be some space that the learnable weights is spanning, and there can be some space where the policy function is spanning. The later one could be described as this one. This kind of distance discrepancy can also happen in supervised learning as well. It is, very natural. Distance in parameter space is not consistent with distance in output space. It is applicable to all neural network, including networks trained in supervised learning. But in supervised learning, a large step might briefly increase the loss, but in RL, an oversized step can cause a performance collapse that is often impossible to recover. So this kind of thing is applicable to both supervised learning and reinforcement learning, but is especially very significantly making performance degraded in case of reinforcement learning, because the training data is self-generated by the current policy. A collapsive policy will only collect poor quality data, leading to permanent failure of the learning process. In supervised learning, even though there is something bad happening in the weight space, we can recover it as we have off-the-shelf data, right? We have off-the-shelf training data so that although there is something bad happen in the parameter space, we can recover such kind of failure cases using external training data. We have lots of training data in supervised learning. But in reinforcement learning, once training becomes unstable, then that might not be recovered, because the target is always from, we do not have off-the-shelf training data, so that the target could be from itself, so that it might not be, the model cannot recover maybe. The discrepancy necessitates an update rule that respects the distance in policy space rather than just mathematical distance between parameter vectors. So there are two limitations in policy gradient: sample efficiency because it's on policy method, and distance discrepancy. It is especially important for RL because the targets are from itself, which is different from supervised learning. And let's see sample efficiency in detail. So sample efficiency for vanilla policy gradient method is poor because policy gradient is on policy expectation. On policy means here, so discard each batch of data immediately after just one gradient step. On policy here, the definition of on policy is here. On policy means agent learns strictly from data collected by its current policy, requiring the data to be discarded immediately after a single update to maintain mathematical validity. That is the definition of on policy. It seems very different from replay buffer, right? We studied replay buffer in DQN. In DQN, the motivation of the replay buffer is kind of securing some training data from the current Q-value network, and then use such kind of collected training data to train the Q network. So that is off policy. Off policy. Off policy means we have some training data in advance, and then we use such kind of training data to train some network. That is called off policy. But PG is on policy. Mathematically, it is on policy by definition. So why PG is an on policy? The mathematical objective of policy gradient is defined as the expected return under the current policy distribution, meaning the trajectories used for the gradient estimate must be sampled directly from the policy being updated. So what this means is that here we have mathematically the policy function is from the current training iteration, not from the previous iteration, or other policy functions. So mathematical objective function is just that it says that policy gradient is on policy, but that makes sample efficiency very poor. So when the policy parameter change even slightly, the previous data no longer represent the current action distribution, making the all data mathematically invalid for computing the next gradient step. And on-policy learning is a requirement where the agent learns strictly from its own current experience to ensure the gradient points in the correct direction for immediate improvement. So this shows that what sample efficiency this means, and that why PG is on-policy. By definition, it's just on-policy, but it makes sample efficiency very poor. So two main approaches to obtaining an unbiased estimate of the policy gradient. There can be two ways. The first one is collect sample trajectories from policy, then form sample estimate. That means a sample, we store some data. We store some data replay buffer with the current trajectory, or we can use current policy, or we can use other policies, but they might make training more unstable. So there can be two ways to obtain unbiased estimate of the policy gradient. So that to improve sample efficiency in policy gradient, we want to use old data to take multiple gradient steps before using the resulting new policy to gather more data. That is straightforward, right? We also consistent with the motivation of replay buffer. We actually want to use old data more than once for the sample efficiency. That is consistent with the motivation of replay buffer. But challenge is that even if it is possible to use old data to estimate multiple gradients, how many steps should be taken? Actually, that is a very serious problem in RL. As I said, that might make policy function very bad, and then they might not be recovered. The policy gradient algorithm are just stochastic gradient ascent with step, and if the step is too large, performance collapse is possible, and we can see this graph. It tries to maximize value function, so that is gradient ascent. If the step size is too large, performance collapse is possible. If step size too small, progress is unacceptably slow. Right step size change based on theta. You can see here. So why this happen? Why performance collapse can happen? It is also straightforward, right? Because let's say in this case, easy way to think about reason is that thinking some extreme case. For example, let's say you set step size like very huge, like step size is 1 million or 1 trillion. If we set step size very large, then the parameters in policy function could be perfectly fitted to the current data from the current policy function, but that might introduce overfitting, right? It's straightforward. So that might make performance collapse, and then it might not be recovered because the target is also from itself. But if step size too large, performance collapse is possible. But step size too small, then that is also different from the motivation of this kind of sample efficiency. We want to make training faster, but if step size too small, then progress is too slow, so that it is different from our motivation. Right step size change based on theta, and automatic learning rate adjustment like advantage normalization or advanced optimizer can help. But this is not very trivial, actually, choosing a step size for policy gradient. This is just an example. Let's say the policy function is when a equals to 1, then here, and a equals to 2, like this. Then if theta is 4, then we have this kind of policy function outputs. And theta is 2, we have these outputs. And theta is 0, we have these outputs, so that even small changes in the policy parameter can unexpectedly lead to big changes in the policy. And the very serious question is that how do we come up with an update rule that doesn't ever change the policy more than we meant to? This is actually motivation of PPO. How can we come up with some fancy update rule that doesn't ever change the policy more than we meant to? How can we do this? That is actually motivation of PPO. And PPO is very stable and widely used. And let's proceed to policy for performance bounds. So for this one, how can we come up with update rule that doesn't ever change the policy more than we want? For this one, actually, we need to measure distance between policy function. Here, performance difference lemma. We need to actually measure this one, so that actually we need to measure distance in policy function, not parameter space, because we studied distance discrepancy, right? So in policy optimization algorithm, we want an update step that uses rollout collective from most recent policy as efficiently as possible, and takes step that respect distance in policy space as opposed to distance in parameter space. And to figure out right update rule, we need to exploit relationship between performance of two policies. And this is performance difference lemma. For any policies, pi and pi dash, the difference in value function could be derived like this one. Expectation of, where trajectory is from new policy and advantage is from old policy, right? And then we can rewrite like this one. This is just a lemma. Where D is like this one. So as you can see, trajectory is from new policy, and advantage is from old policy. So with this kind of lemma, we can measure relationship between performance of two policies. So based on this lemma, we will study how can we use this kind of performance bound to get some right update size, step size. So let's first interpret this lemma. What does this mean? So this lemma mathematically quantifies the performance gap between a new policy and an old policy using advantage function of the old policy. As I said, It tries to measure performance gap between new policy and old policy, advantages from old policy, but the trajectory here. Trajectory means a consecutive tuple of state and action. The trajectory is from new policy, but the advantage is from old policy. And implies is that if we can find the new policy pi dash that consistently chooses action with positive advantage, the overall performance is mathematically guaranteed to be higher than J pi. Let's see this example first. I think this is not very straightforward to understand. Think of your overall grade, J. J is a value function, so that it might be your grade. Your performance. Improving your grade is simple. You just need to keep your daily study efficiency, action slightly higher, advantage positive, than your usual average. So advantage is the Q minus V, right? So that you want to make advantage positive than so that your Q function is better than your average value function. The difference in your final grade here, difference in final grade is exactly equal to total sum of extra effort you put in every day throughout the month. Can you understand this example? This example, I think, once you see this example, you can understand this equation, I think, easily. So you try to, as I say, try to measure difference between new policy and old policy in terms of value function. And implies that if we can find a new policy pi dash that chooses action with positive advantage, the overall performance is mathematically guaranteed to be higher than the value function of old policy. The mathematical structure shows that the performance of a completely new policy can be evaluated by simply summing up how much better its individual decision are compared to current baseline. We learned baseline, right? Baseline is just so you can see its value function. We will not study how to derive this, but you can understand this equation with this example. It tries to compare new and old policy. And how can we use this policy improvement where pi dash represent new policy and pi represent the old one? Let's see this one. So we want to maximize, let's see this one. It's a little bit abuse of notation. So this is not the mathematical equal. We are just interested in getting new policy function pi dash. This is so that we can use this relationship, and then we derive this one, right? We derive this one from previous equation. So that the new policy that can maximize its value function can be obtained with this equation. So this is suggestive but not useful yet. Nice feature of the optimization problem defines the performance of pi dash in terms of the advantage from pi. But the problem is that it still requires trajectory sample from new policy here. As I said, the trajectory is from new policy, but the advantage is from old policy. The problem is that we can access to old policy. But we cannot get trajectory data from new policy. So here, why we need trajectory from old policy? So from now on, we will actually do some mathematical tricks to change this one. To change this tau is sampled from new policy to tau is from old policy. We will do some mathematical tricks and introducing some new things to change the trajectories, the original trajectory sample from new policy, but now we will change it to trajectories from old policy using some mathematical stuff and introducing new stuff. So why are we going to do this? Why are we going to get trajectory from old policy pi? But the agent cannot collect trajectory from the new policy pi dash. That policy is still being optimized and does not yet exist in a finalized form. Using trajectories from old policy pi for data reuse, significantly improving sample efficiency by avoiding the need for new environment interactions at every gradient step. As I said, here the motivation is improving sample efficiency. And let's say we did one rollout, and then we have all the policy here pi, and then we can update. We can perform gradient update. We can perform the gradient ascent multiple times, right? With the what we have once we have roll out, then we have data. It's like replay buffer. We have data in replay buffer, and then with this data sample from replay buffer, we perform the weight update more than once, right? Multiple times. That is also, almost the same as this one. We like to, from the data from rollout, we want to use this data to update our policy function more than once. But here the data, if data is from new policy, then every time we update, we perform gradient ascent, we need to collect data, right? Then every time gradient is updated, we need to perform rollout. That is actually make training very slow, and that is why PG is on policy and it's very slow, so that we want to reuse data. Reuse data means trajectory should be from all the policy. That is the reason why we need trajectory from all the policy. If trajectory is from new policy, then it is just the same as the original PG, original policy gradient, that is on policy. We want to introduce some off-policy thing in PG, so that we want to reuse data from rollout from previous old policy function. That is the motivation of why we need trajectory from all the policy pi. Right? It is consistent with the sample efficiency that I told you just before. So using trajectory from all the policy pi for data reuse, significantly improving sample efficiency by avoiding need for new environment interaction at every gradient step. So new environment interaction at every gradient step, that is the original PG, which is strictly based on policy learning strategy. For every gradient step, it needs to perform rollout and then gather trajectory and then gradient update only once, and then also again interact with the environment to get training data, and then perform gradient step only once, that is on policy. But we'd like to reuse data from all the policy. That is motivation why we need trajectory from all the policy. It enables off-policy optimization here, right? Off-policy optimization, where the agent can perform multiple updates on a single batch of collected experience. The transition transforms a theoretical ideal but impossible objective into a practical optimization problem that can be solved using existing recorded data. Right? Recorded data means data from all the policy and off policy. They are also they mean almost the same things. So that we want to change this one. Tau is sampled from new policy to tau is sampled from all the policies, so that we can reuse tau. We can fix the sample tau from all the policy, and then we can perform gradient update more than once. That becomes some kind of off policy, right? To improve sample efficiency. And in terms of discounted future state distribution d pi, defined by like this, and we can rewrite relative policy performance identity. This is just a performance difference lemma, and then we can rewrite this one. So far, it is, okay. So far, it is performance difference lemma, and then we can introduce some important sampling tree statistics. So here, we can rewrite this one into this one, right? Just expectation is just a multiplication of probability and data, right? So that state is from this one, and then probability is from this one, and then data is this one. We can just rewrite this one. And then we can introduce this one. It's just a 1, right? It can cancel to be 1. But we introduce this one, and then we can rewrite like this. So this becomes new probability. Originally, probability was from new policy, But here, with the importance sampling trick in statistics, we can change the probability from new policy to old policy, right? So that we can see action is from old policy. So we made a one step. At the first time, both state and action are from new policy, so that the training is strictly on policy. We could not reuse data from old policy. But now we made a one step. Action is from old policy, right? By introducing this one. But we have remaining problems. State is still from new policy. We need to change the state also from old policy. Then we can say that we can reuse data from old policy. How can we change state to old policy? Unfortunately, it is not easy. We didn't make approximation. Action, by introducing this one, action can be replaced with the old policy. There's no approximation, but state, unfortunately, we need to make some approximation. So what if we just said new policy and old policy are almost the same? In this assumption, then we can sample state from old policy, but the assumption is that policy function, new policy and old policy function should be almost the same. That is assumption. Under this assumption, we can change state is also from old policy, then it's done. The trajectory is from old policy. What does this mean? What does it mean is that we can reuse training data from old policy, then we can improve sample efficiency, which is one of the limitation of policy gradient, right? But how can we say these two policy functions are almost the same? That is also relevant to the distance discrepancy problem that I introduced in the previous slide. The distance in parameter space is different from different distance in policy space, right? So that we need to introduce something to measure how those two policy functions are close, right? That is relative performance, policy performance bounds. Let's see this one first. Turns out that this approximation is pretty good when these two policy functions are close. But why and how close do they have to be? That is about relative policy performance bounds. But there were two limitations policy gradient, right? The first one is sample efficiency. How did we address it? We addressed sample efficiency by changing all trajectories are from old policy. Mathematically, we can replace action to old policy, and with the approximation, we can change state from old policy, so that now the first limitation is addressed. We now can use training trajectory from old policy, so that we improve sample efficiency. But remaining problem is the distance discrepancy. Distance in policy function is different from distance in parameter space. So we need to address that, right? So that we can say whether the two policy functions are close or not. Because this approximation is only hold when the policy functions are very close. So that we introduce this one, relative policy performance bounds. This is approximation, and then with this approximation, let's say, then J pi dash could be approximated with J pi plus, right? So we can just plug this into here. So that the performance, the difference of these two things is upper bound with this one. C is just a hyperparameter. It is not constant. It can be adjusted in the learning training iteration. We will see how to set this C in next time. Anyway, C is just kind of some parameter, and then here now we have upper bound of this one, and this should be small, right? This should be small, but the important thing is that we finally have a something that we can measure distance between two policy functions using K divergence. If policy is close in K divergence, the approximation is good. That is the conclusion of this inequality. So the K divergence is just some way to measure distance between two distributions. So this is definition of K divergence. For probability distribution P and Q over a discrete random variable, of course for continuous we can change the sigma to integral, right? The definition of K divergence is like this: Px log Px Qx. So for the same distribution, distance 0, and as distance is always positive, and it is not symmetric. K divergence is actually very widely used when measuring distance between distributions. One thing that you might know is we use this K divergence when training VAE, variation autoencoder. We want the latent space of VAE should be normal Gaussian. So this is encoder, this is decoder, and then we compute K divergence between normal Gaussian, right? This is a typical training strategy to train VAE. Anyway, so K divergence is very widely used to measure distance between distribution. And the K divergence between policy could be, like this one. What did we gain from making that approximation? So here, then the distance between two policy could be like this. Now it's done. Now all things are set. So trajectory is from now the original one. Let's see the original one. Original one, trajectory was from new policy, so that we could not reuse training data from all the policy. But now trajectory is from all the policy, so that we can reuse training data from all the policy, which can improve sample efficiency. This is something we can optimize using trajectory sample from all the policy. This is actually really important, really good thing. We can improve sample efficiency of policy gradient. Similar to using importance sampling, but because weights only depends on current time step and not preceding history, they don't vanish or explode. This is not a very important thing, but the original importance sampling in statistics is that we need to perform this one, pi. You know, pi is the multiplication. This is multiplication. Originally, it should be t goes to 0 to target. So that we need to keep multiplying all these kind of things, but that could introduce vanishing explode, right? If this one is larger than 1, then it might introduce exploding. If this is smaller than 1, then this could introduce vanishing, but as here, weights only depends on current time step. They're only t, right? So they don't vanish or explode. Okay, so the important thing is that, as I said, we like to address the limitation of policy gradient. The first one is sample efficiency, and second one is distance discrepancy. We address sample efficiency by changing trajectory from new policy to old policy. What this means is that we can, now the sample is from old policy, so that we can reuse training data from old policy. That is consistent with the motivational replay buffer, so that we kind of introduce something similar to the replay buffer in a mathematically safe way. Originally, a mathematical definition of policy gradient does not allow introducing replay buffer, but with mathematically safe way and some approximation, we can now introduce something similar to replay buffer in policy gradient. We can improve sample efficiency, and the distance. Now we can measure distance between two policy using this one, right? Under this assumption. So when training the policy function with PPO, we set this kind of C, we adjust this kind of C so that we, in training iteration, so that we make sure that the new policy, the updated policy and old policy are not very far. We make some clip, we introduce something that we want our updated policy is not very far from new policy. so that we can prevent this kind of drastic change in policy function, right? We can prevent this kind of drastic change in policy function. That is the motivation of PPO and how we address the problem in policy gradient. Okay, and any question you have? I think it's not very complicated, okay?